Now we want to talk about derivative of, I want to talk about more about derivative of vector valued functions. So again, a vector valued functions is something like f from R to say R2. By derivative, I mean we should take derivative of each part of the function, each component of the function. Okay. So let's see. So suppose f of x is equal to, okay, let's start with something not very hard to make sure you know the basic rules. Square root of 4 minus x squared. And the second component, suppose, is minus x over 4 minus x squared. And the question is, what is derivative of f? Okay, think about that for a few minutes, compute the derivative. So we should take the derivative of the first component, and then we should take the derivative of the second component. Okay, the first component is the square root of 4 minus x squared. I should just review a few things. The idea is something named chain rule. I'm mentioning chain rule because it's going to be one of very important things in chapter 3 and 4. We are going to see higher dimensional version of chain rule. So I'm going to first review what does chain rule mean. So here we have, in some sense, we have a function here, but we also can think about it as composition of two functions. So if I name this function g of x, I can think about g as composition of two functions. It's like first I have x. It's like first I compute 4 minus x squared. And then after that, I would compute the square root of 4 minus x squared. It's like there are two steps in computing this function. And I can really write down this function like that. I can say, I construct two functions. Let's call one of them h. Let's call the other one k. I would define h of x to be 4 minus x squared. I would define k of x to be square root of x. Okay? The point is that g of x is equal to k o h of x, is equal to composition of these two functions. In other words, k of h of x. Well, what is that? It's k of anything. Well, see, when k of x is the square root of x, it means k of anything is the square root of that thing. So k of h of x would be square root of h of x. But what is h of x? Well, it's 4 minus x squared. So the point is that, and that's what g really is. So the point is that sometimes we can write down a function as composition of two other functions. Okay? So g of x can be written as k of h of x. Now, the important thing is that whenever we are in this situation, we have a formula for derivative of g. Derivative of g is actually equal to k prime of h of x times h prime of x. Okay, let's see, for example, how does it work in our case. In our case, the function g of x is square root of 4 minus x squared. I said we can write it as k o h of x, where h of x is 4 minus x squared, and k of x is the square root of x. Okay, This implies j prime of x is derivative of k. Okay, what is derivative of k? Well, square root of x is the same as x to the power 1 over 2. So derivative of k would be 1 over 2 times x to the power 1 over 2 minus 1, which is 1 over 2 x to the power negative 1 over 2. That's k prime. 1 over 2 x to the power minus 1 over 2. But note that rather than x, we have h of x here. So we should write h of x here. But what is h of x? It's 4 minus x squared times h prime of x. What is h prime? Well, h was 4 minus x squared. Its derivative of 4 is 0. Derivative of minus x squared is minus 2x. That would be the derivative of this function. We can simplify it a little bit. We have 1 over 2. Here we have 2. If we multiply them, we would get 1. So it would be minus x. And because here the power is negative, we can take this function to denominator. It would be 4 minus x squared to the power 1 over 2, which is the same as the square root. So that would be derivative of the first component of our function. Now we should compute the derivative of the second component. So what is the second component? Minus x over 4 minus x squared. Here we have the quotient rule, a over b. What is derivative of a over b? It's derivative of a times b minus a times derivative of b over b squared. That's the quotient rule. Okay, so first we should take derivative of numerator. Derivative of minus x is minus 1. Yep, I can go back. Here, okay, can I go back? Is it good? Okay. So we should first take derivative. So what does this thing tell us? This quotient rule tells us when we have a over b, the derivative of this fraction would be derivative of numerator times denominator minus numerator times derivative of denominator over denominator squared. So here, derivative of numerator, derivative of minus x is minus 1. We should multiply it by denominator, would be 4 minus x squared minus, well, numerator is minus x times derivative of denominator, 4 minus x squared, which would be minus 2x. Derivative of 4 is 0, and derivative of minus x squared is minus 2x. We should divide it by 4 minus x squared squared. We can simplify this thing. Minus 1 times 4 minus x squared. Well, it will be x squared minus 4. Here we have negative times negative. They will cancel each other. Both of them will become positive. And we have x times minus 2x. The result would be minus 2x squared. In denominator, we have 4 minus x squared squared. We'll leave it like that. Okay, we can continue simplification. We have x squared minus 2x squared. Well, that would be minus x squared. And then there's minus 4 divided by 4 minus x squared squared. That would be the derivative of the second component of our function. Now, if we write them next to each other, that would be the answer. So the derivative would be the derivative of the second part, which we compute, and that's what we got as the answer. And then the derivative of the second part. As you can see, again, it's a vector. It has two components. So for example, if they ask us what is derivative at, say, 0, we should just plug in x by 0. We should let x to be 0. Well, here we would get 0 over, here we would get square root of 4 minus 0, which is the square root of 4. Here we would get 0 minus 4. Here we would get 0 over 4 squared, which is 16. Okay, 0 over anything is 0. Minus 4 over 16 is minus 1 over 4. We can simplify it. And we would end up with a vector. So the derivative of this function at every point is a vector itself. Any question here? Okay. Okay, let's consider another example. Oh, there is a question. No, there isn't a question. There was a comment which there is no question. Okay, let's consider another example. Well, let me see how much I want to proceed now. We have 5 minutes. Oh, we have 5 minutes. Maybe it's better not to go any further. I would speak about functions of several variables on next week. So let's look at the question you asked, the second question of the exam. Let P be 2, 3, 1. Let Q be, yeah, we have class before the exam. Let Q be 2, 2, 2. The line which passes, consider the line which passes through P and Q. Does it intersect this other line? X minus 1 over 2, y over 3, z plus 1 over 4. Do they intersect or not? Okay, let's find out the line which passes through P and Q. Well, first of all, so we have P and we have Q. P is somewhere, I'm just putting these points randomly. We can look at the vector which goes from P to Q. That would give us the direction of the line, right? We want to find a line which passes through P and Q. If we look at the vector PQ, that would give us the direction of the line, which is actually Q minus P. So it's 2, 2, 2 minus 2, 3, 1. So it would be 2 minus 2, 2 minus 3, 2 minus 1, which is 0, minus 1, 1. That would be.
All right. What is
direction.
The question asking us to do?
Well, the question, it was your homework. And so the question was, consider these two lines. Is there, these lines, do they have intersection or not? So does the line which passes through P and Q intersect this line? So it was in the practice exam. So it seems, well, I got a few questions that you are not sure about this question from the practice exam. So I'm solving that now. So first I should write down the equation of the line which passes through these 2 points. And in order to do that, I need the vector in the direction of the line. That would be, this is going to be the vector in the direction of the line. Now, whenever we have a point on the line here, P, for example, and the direction, we can write down the equation of the line. The equation would be x, y, z equal, well, this point P, 2, 3, 1, plus these numbers times t, 0 times t, minus 1 times t, plus 1 times t. So it would be 2, 3 minus t, 1 plus t. Okay, that would be the equation of this line. Okay, now I want to see if this line here in the red box, the question is if this line intersects this line, the line in the blue box. There is something very special about this line, and that's the fact that x is always equal to 2, as you can see. Okay? So x is always equal to 2. Look at the line we have here above, the line in the blue box. If they want to have intersection, x should be equal to 2 here, right? If they have intersection, because the line in the red box, its first component, the x component, is always 2. If they intersect somewhere, that point, x will be 2 for the blue line too. So we would have 2 minus 1 equal 2 equals y over 3 equals z plus 1 over 4. Okay, let me write down that thing in the next page. So 2 minus 1 over 2 equals y over 3 equals z plus 1 over 4. That's one line. The equations for the other line was x equal to 2, y equals 3 minus t, and z equals to 1 plus t. That's the equation for the other line. I could write the symmetric equation, or I could write the parametric equation. Both works. So here x is equal to 2. What we get here is that 2 minus 1, which is 1 over 2, is equal to y over 3 is equal to z plus 1 over 4. Now we should exploit this equation. So look at this thing. 1 over 2 is equal to y over 3. Therefore, y, well, if I multiply both sides by 3, y would be 3 over 2. That's y. Now, I should exploit the other part of this equation, the fact that 1 over 2 is also equal to z plus 1 over 4. So 1 over 2 is equal to z plus 1 over 4. If I multiply both sides of this equation by 4, I would get 4 over 2 equals z plus 1. In another terms, z plus 1 would be equal to 2, which means z is just 1. So if there is an intersection point, we still don't know, but if there is an intersection point, the intersection point should be this one. X is 2, y is 3 over 2, and z is 1. But is it really a valid intersection point? Well, if it is, it should satisfy the equations of both lines. So I should see if it satisfies this parametric equation or not. That's the final step. So we have a point, 2, 3 over 2, and 1. And I want to see if it satisfies the parametric equation for the other line 2 or not. Okay, it's kind of simple. So 2 is equal to 2. So x, well, this point, let's call this point A, says x is equal to 2. Well, that's good. Here, we also say x is equal to 2. The second component says y is equal to 3/2. Okay. What does this equation say about y? It says y is 3 minus t. Okay, this can hold if t is equal to, well, we can solve this equation if t is equal to 3 minus 3/2. What is that? Well, that's 3/2 if I solve this equation. So this equation tells me t is 3/2. Okay, that's what it tells me. What about the last component? The last component says z is 1. But this equation here tells me z is 1 plus t. So 1 and 1 plus t should be equal. Well, what does it say about t? It says t is 0. Well, how can it be? One equation says t should be 3/2. The other equation says t is 0. It can't be, not possible. Therefore, no intersection points. Therefore, these two lines, they don't have any intersection. Any question? If we write down the symmetric equation, we still get the same thing. The symmetric equation still would tell us x is always equal to 2. Yes, I can go back to the previous page. This is the previous page. I used this fact that the second line tells me x is always equal to 2. And because, well, the other line, the equation was x minus 1/2 equals y/3 equals z plus 1/4. I plugged in x by 2. And then it becomes 1/2. I used that to compute the values of y and z, because 1/2 should be y/3. That gives me y. And 1/2 should be equal to z plus 1/4. That would give me z. So I have x, y, and z. I should only check if this point, x, y, and z, if it is a point on this other line too. Well, if it was 2 plus 2t, we could do the same thing. We should have plugged in, well, you see here, it would have been a slightly harder question, which I didn't give that question to you. But, okay, let me ask, there are 3 questions. Let me answer them one by one. So rather than plugging in x by 2, I would have plugged in x by 2 plus 2t. If, for example, someone has asked, what if rather than 2x was 2 plus 2t? What would have happened? Well, rather than x here, I would have written 2 plus 2t. I could still solve y and z, but they would have some t in them. So y would have been, say, 2t plus 1/2. Well, I have a good idea. Let's pause this thing. I would solve this for another value, which x would be 2 plus 2t. Let me see if there is any question about the exam. Answer that, and then I will come back to this. What if my line, the question is, what if my line was 2 plus 2t, y was 3 minus t, and z was 1 plus t? Well, the answer is that just like always that we have class, you should use Blackboard. Through Blackboard, you would log into your Zoom. Just like always that we have class. You should just turn on your webcam. Okay, that's one line, and the other line is x minus 1/2 equals y/3 equals z plus 1/4. Now it's a slightly harder equation. Yes, you should open your camera on Zoom. There would be people proctoring you, right? They would, because because it's the exam, they would do that. Well, I mean, right now, here we want to solve, we want to see if these two lines, if they have intersection or not. What I would do, I would use one of these variables, say x equals 2 plus 2t, and I would plug it in into the other equation. So it would be 2 plus 2t minus 1 over 2 equals 1 over 3 equals z plus 1 over 4. Okay, let's simplify it. 2t plus 2 minus 1 is plus 1 over 2. It should be equal to y over 3. What does it say about y? I can compute y from here. I can multiply both sides by 3. It says y is 3 times 2t plus 1 over 2. Okay, on the other hand, this quantity should be equal to z plus 1 over 4. So 2t plus 1 over 2 should be equal to z plus 1 over 4. What does it say about z? Well, I can multiply both sides by 4. I would get 2 times 2t plus 1, and then I should subtract 1. It would be 4t plus 2 minus 1 is 4t plus 1. Now, note that we have a value for y and x already here, 3 minus t and 1 plus t. And now we found new values for y and t. We found y should be 3 times 2t plus 1 over 2, and z should be 4t plus 1. These things, they give us equations. We love equations actually in math. So one of them tells us y is 3 minus t, and z is 1 plus t. Then the other computation tells us y is equal to 3 times t plus 1 over 2. Actually, 2t plus 1 over 2. And the other one tells us z should be 4t plus 1. Now, I can use the first equation, this equation, to find t. What is t? Well, I can multiply both sides by 2. So 2 times 3 minus t would be 3 times 2t plus 1. Therefore, 6 minus 2t should be 6t plus 1. Therefore, 8t is 7. Therefore, t is 7 over 8. Now let's look at the second equation. 1 plus t should be 4t plus 1. Therefore, 3t, oh yeah, fine. It's not minus 1, thank you. Therefore, 3t should be equal to 0, which means t is 0. These two don't agree, do not agree. Therefore, there is no answer to these equations. Therefore, there is no intersection point. If they agree, it means there is an intersection point on these lines. So there is no intersection point. Okay, that's it for today. If there is no question, we can finish now.
Couldn't you just plug in the t's on the beginning and then make it like equal to each other?
Where? Let me go back.
Because the original x, y, z equation, they all had like t's in them. So could you just substitute like the y and the z for the parametrics?
Well, I can, but I want to make sure you are referring to a correct substitution. Let me find where I wrote the original equations. Oh, they're here. So I have these two equations. I have this red box and I have this blue box. What do you want to do?
So could you just substitute like 3 minus t for y and 1 plus t for z?
Oh yeah, you can do that. If you do that again, you would get two equations. You would have x minus 1 over 2 equals y over 3. After substituting them with these t values, and then you would have another equation for y over 3 equals z plus 1 over 4. Again, if you, instead of y, if you write 3 minus t, and instead of z, if you write 1 plus t, you would have another equation. You should solve this one to find the value for t. You should solve this one to find the value for t. If they agree, it means there's an intersection point. If they don't, it means there isn't any intersection points.
So you could use either method.
Yeah, exactly.
Thank you. I also
Yep,
have
you're welcome.
homework if you're willing to stay for a bit.
Mm-hmm. Yeah.
So my first question is, for the difference between the angle between two vectors and the angle between two planes, I think in notes we wrote that for the angle between two planes, it's the same thing as the angle between two vectors, but the textbook says that you take the absolute value of two normal vectors, but we did in class, we didn't take the absolute value, so we got...
No, I don't, well, you don't, both things are correct, there are slightly different conventions. So I don't really expect you to do that. The point is that when you have two vectors like this, you can kind of continue them. So this would be the angle between the vectors, right?
Right.
But there is another angle here, which is, this one is not really the angle between vectors. We usually, the red one, because they have direction, we take the red one to be the angle between two vectors. Now, if you have planes, one of them is like this, the other one is like this. If you continue these planes, you would see the same confusion. You can take this one to be the angle between the planes, or this one, right? You see there, for example, if the red one is 60, the other one would be 120. The book says you should take this one to be the angle between them. That's why it takes the absolute value. What I said is that I would accept both of them. It's fine for me. I think both 60 and 120 are the answers.
For number 5, I'm talking about.
Sorry?
Oh, I was just talking about number 5 because then I did get 2 angles.
Yeah, so whichever you write in the exam is correct. I would accept that. If you write down what I said or what is in the book, I would accept both.
Okay, thank you.
Yeah,
I have another question too. Or in the textbook on page 800, 801, they give like basically a spreadsheet of like the 6 quadric surfaces. Under like each section, they give like the traces and the planes, and more classifications like ellipses and hyperbolas and parabolas. Would we have to do, or just the main surfaces?
Well, I mean, the surfaces which you are supposed to, I expect you to know, I think I wrote them in the notes I gave you. And the surfaces I expect you to know are the cylindrical surfaces, and the quadric surfaces I expect you to know is a sphere, ellipsoid, hyperboloid of 1 sheet, hyperboloid of 2 sheets, elliptic cone, elliptic paraboloid, hyperbolic paraboloid, which is saddle, and surface of revolution. Which I guess is exactly what, these are the things which are also in the book. If you look at the note number 3, I wrote a list of things you need to know before the exactly before the homework questions, before the exercises.
Okay, good, because I think the table has extra information like
yeah, no, you don't need to memorize those extra information.
Oh, okay, thank you.
Yep, you're welcome.
I also have another question about just in general for homework 3. So for the drawings from 6.1 to 6.8,
Uh-huh.
I put tick marks for some of them, but not for like 6.1, for example. Should I change that?
Would you say again? I didn't hear you for a second.
Oh, sorry. For some of the problems, I put tick marks to like show reasons, but for 6.1, I sort of just drew like the outline of it.
No, it's okay. I'm not going to be very hard on you about these drawings. It's just I want to make sure you understand what this equation is representing, not more than that.
So we don't have to like
No.
cross sections of like the circles.
No, it's not necessary. No.
Okay. Also,
Yeah.
one last question. If we were to draw like a cross section of a hyperboloid of one sheet, would we have to like look at the equation with the coordinates and like determine where the center is and like how thick it would be?
If you want to use, if you want to use cross sections to do that, yeah, you should look where it is. And so, for example, you would fix a value for z. It would be something two-dimensional. It would become, for example, it becomes a unit circle, let's say, at the origin, and then you would draw a unit circle at the origin. I don't expect you to be very accurate, but you should understand, for example, for different values of z, if you look at the cross section, if the radius is increasing or decreasing, you know, so it almost should be at least correct. I don't expect you to be very accurate, but I expect you to at least know where the surface is, or almost what is the radius at each point.
So for 6.4 on the homework, for example, would the center be 1,
0,
-3?
Yeah. So this would be 1, 0, -3. It would be here. That the center would be here, right? And then what is the type of the surface?
I said it was hyperboloid of one sheet.
It's hyperboloid of one sheet. And what is the direction?
Going in the z direction.
So I expect you to at least draw something like this.
So would we have to talk about the significance of the like over 4 over 9, because in the problem it says like
not here, not in this hyperboloid, but for example, if you are drawing an ellipsoid, there you need to, because in ellipsoid, as I explained before, the numbers like x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, these numbers are kind of radius in each direction. So they have a more obvious significance than the hyperboloid.
But you wouldn't have to know about, like, you wouldn't have to talk about the significance of those numbers when you're drawing the diagram.
No. So let me tell you two axioms. One is that I would only expect you to say things I told you in the class. And second is that definitely in the exam, I would be clear about things I want you to write. So if you review everything I said in the class, and if you read the questions in the exam carefully, there shouldn't be any problem.
Also for 6.4, when it says the equation's equal to 9, does that mean the radius is 3?
Well, not necessarily, because you have some denominators there. So the idea was that you should divide everything. Well, you have an ellipsoid or first of all, 6.4 is not an ellipsoid, right? So you should be careful about what do you mean by radius here.
Right. So I'm not sure what the equal 9 means.
Well, the point is that you mentioned if we can use the cross section. So for example, here the center is 1, 0, -3, right?
Right.
So the center is here. One idea is that we can look at this plane, z equals to -3, and see the intersection of the surface with this plane. Okay? If we do that, if z is minus 3, we get x minus 1 squared over 4 plus y squared plus, sorry, minus z plus 3 squared over 9 equals 9. Now, if z is minus 3, z plus 3 would be 0. So this term would disappear. If I'm only looking at this plane, z equals minus 3.
Mm-hmm.
And then the equation which remains is x minus 1 squared over 4 plus y squared equals 9. Now, if you divide everything by 9, you would get x minus 1 squared over 36 plus y squared over 9 equals 1. This is actually equation of an ellipse. Which
So
in direction of x, the radius is 6, in the square root of 36. In direction of y, the radius is the square root of 9, which is 3. So in this plane, you would have something like this. And then you can look at another plane, and then, for example, z equals to 0. You would get something else, and then you can connect them.
So you'd only have to show the cross section of like z equals -3.
Yeah, as I said, I don't expect you to be very accurate. If you just look at one plane or two planes, you would get a feeling about how the surface would look like. And then you can give just a sketch of that.
Okay, thank you.
Yeah, one plane is usually enough. Yeah, that's good. Yep, you're welcome. Any other question? Okay, then if there isn't any other question, that's it for today. Study well. Good luck with the exam. Bye.